All right, in this video, we're going to look at taking a matrix and raising it to some power. It has quite a few applications. It can be pretty computationally expensive unless you perform the kind of mathematical moves that we'll see in this video. All right, so let's just take this matrix A, 1, 2, 3, 4, and let's square that matrix. Squaring that matrix means doing A times A, and that's a matrix-matrix multiplication, and we know by definition, matrix times a matrix is repeated matrix vector multiplications. So we take the left matrix and multiply by the first column of the right matrix. And we also take the left matrix and multiply by the second column of the right matrix. And we get those two results. And those form the columns of our resulting matrix. Now let's look at when we take a diagonal matrix. Remember, a diagonal matrix is when you have zeros on the non-diagonal. And on the diagonal, it could be 0 or non-zero. So in this case, we have the matrix 5, 0, 0, 3. And if we square that diagonal matrix, notice when you're calculating the first column of our result, you have the left matrix times the first column of the right matrix. So you do 5 times the first column plus 0 times the second column. And 0 times the second column is a 0, 0. So you really just have 5 times the first column, which is 25, 0. And likewise, for finding the second column in the result, you'd have 0 times the first column plus 3 times the second column. So you get 0, 9 for that second column of our resulting matrix. And the main point here is when you square a diagonal matrix, you're actually just squaring the entries in that diagonal matrix. So remembering this fact about diagonal matrices, you don't actually have to do all that computation of matrix-matrix multiplication. You can actually just raise the entries in your matrix to the power that you're working with. So nice and efficient compared to a general matrix being raised to a power. Now let's look at what happens when you take a general square matrix A and multiply it by a diagonal matrix D. So here's our A and D from before. And we have to do the two matrix vector multiplications to get the two columns in our result. So there is A times the first column of D, just calculated by doing 5 times the first column of A plus 0 times the second column of A, which really is just the 5 times the first column of A. And likewise, we find the second column in our result by doing A times the second column in D. And really, you just have 3 times the second column of A. And these form the columns of our result of A times D. And notice the columns in our result are just scaling the columns of A. And we're using the diagonal entries 5 and 3 as the scalar multiples. Now let's summarize those properties of diagonal matrices that we just saw. If you have a diagonal matrix where the entries are D1 and D2 on the diagonal, then if you raise that diagonal matrix to some power, really just taking the entries and raising it to that power. Also, if you have a matrix A multiplied by a matrix D, and you can write the matrix A in terms of its columns. Maybe there's just 2 columns, so A1 and A2. All you're really doing in that computation is scaling the columns of A by the diagonal entries, D1 and D2. And these properties hold for any size diagonal matrix. So you could have like a 10 by 10 diagonal matrix. So any square matrix that's a diagonal matrix, these properties hold. All right, now we're ready to talk about this idea of diagonalization. What is diagonalization? Well, an n by n matrix, so a square matrix, A, is diagonalizable when there exists an invertible matrix P such that A equals P times D times P inverse, where D is a diagonal matrix. In other words, we can rewrite our matrix A as a product of 3 matrices, and the middle matrix is a diagonal matrix, and the right matrix is the inverse of the leftmost matrix. Now here's an example. If we have this matrix 7, 2, negative 4, 1, so this is our matrix A, it is possible to write this as a product of 3 matrices, P times D times P inverse. Notice the middle matrix is a diagonal matrix, and the rightmost matrix is the inverse of the leftmost matrix, P. Now, why would we do this right? It looks like we just complicated this matrix A, right? A looks simpler than a product of three matrices, P, D, and P inverse. But notice if you want to raise A to some power, whatever application you're working in, say if you want to cube A, well, that's A times A times A. Well, since A can be written as PDP inverse, we'll rewrite A times A times A as PDP inverse times PDP inverse times PDP inverse. Well, that looks pretty messy, but notice there's two spots in here that simplify very nicely. Maybe stop the video and try to see how this could simplify. But where that happens is P inverse times P, right? That happens twice in here. I'm allowed to rearrange the parentheses so I can really do P inverse times P first instead of having the PDP inverse being grouped together first. But do you remember what P inverse times P is? Well, that's the identity matrix. An identity matrix times another matrix doesn't affect anything. It's like multiplying by 1. It returns the same thing. So those P inverse times P's can just disappear. They're not really doing anything. So you can simplify it as P times D times D times D times P inverse, which is really just P times D cubed times P inverse. And remember, raising a diagonal matrix to some power is very nice. It's very quick because you're just raising the diagonal entries to that power. And this holds true in general. If you raise a matrix A, or this matrix A, to the power K, then you just really have to do P times D to the K times P inverse. When K gets really big, like if K was 100, well, then you do D to the 100, which is just raising the diagonal entries to the 100, which is nice and quick. And then you just have to do two matrix multiplications to figure out P times D to the 100 and then times P inverse. That's going to be a lot faster than doing A to the 100. In other words, A times A times A times A, which would end up being 99 matrix multiplications. So if you're able to diagonalize a matrix, then raising that matrix to a power is a lot easier to do if you diagonalize it first. But you're probably wondering, what is matrix P and matrix D? Where do those come from? Well, that's what we'll discover here now. All right, let A, P, and D be 2 by 2 matrices. Let's look at 2 by 2 first, but you can easily generalize this to n by n matrices. But let P1 and P2 be the columns of P, so the first column and the second column, and let D1 and D2 be the diagonal elements in D. All right, so if we have A is equal to PD P inverse, well, we can rearrange that equation by multiplying both sides of the equation by P on the right, right? Because then you'd have A times P on the left side of the equation. On the right side of the equation, you'd have PD P inverse times P, but P inverse times P is the identity matrix. So the right-hand side would reduce to P times D. So to get that second equation, I essentially just multiplied both sides on the right by the matrix P. Now I'm just going to rewrite that equation by writing P in terms of its columns and the matrix D in terms of its entries. Now we see that the left side of the equation is just a matrix multiplication, and by definition that's doing several matrix vector multiplications to get the new columns of the resulting matrix. So left side turns into the first column being A times P1 and the second column being A times P2. Then the right side of the equation, remember, this is just a matrix times a diagonal matrix, which we showed earlier to just be scaling the columns of our left matrix. So it'd be D1 P1 and D2 P2 as our new columns. So this is the simplified version of what I just said. We have the left side being AP1, AP2 equaling DP1 and DP2 as the new two columns of those matrices. Now all we have to do is equate columns, right? AP1 is equal to DP1, and AP2 is equal to D2P2. That's just equating the first columns and the second columns. This would be a great spot to stop and think about this last statement. What does this mean? What would D1 and P1 be? And what would D2 and P2 be? Do you recognize these equations? Well, let's just think about the first one, AP1 equals D1P1. P1 is a column of our matrix P. You can think of it as a vector. So we really have A times a vector is equal to a number times a vector. That's how we defined the eigenvalue and eigenvector. So D1 and D2 are eigenvalues of A, and P1 and P2 are eigenvectors. We've reduced this diagonalization problem into solving for the eigenvalues and eigenvectors of the matrix A. That's pretty neat, and this be, again, a great spot just to stop the video and relook at all of this math to see if it makes sense to you. The big idea here is, how do we diagonalize? We'll find the eigenvalues and eigenvectors and go through these mathematical moves to make sure that all makes sense, right? Start with the first line of the equation, and go all the way down to make sure you see how that AP1 equals D1P1 and AP2 equals D2P2. And one last note, for a square matrix to be diagonalizable, we need to have one condition met. Can you think of what that condition is? Well, the matrix P that consists of your eigenvectors, that matrix needs to be invertible. So this only works if P is invertible. If P is not invertible, then we can't write A as PDP inverse. And we've seen certain matrices that are not invertible. A way we can tell if it's invertible or not, we take our matrix and reduce it using row operations. And if you do not get the identity matrix after reducing that square matrix, then that matrix is not invertible. So if your matrix consisting of eigenvectors does not reduce to the identity matrix, then your matrix A is not diagonalizable. All right, let's look at an example. If you have this 2 by 2 matrix, 7, 1, 3, 5, and you want to diagonalize that matrix, well, in the previous video, we saw how to find the eigenvalues and eigenvectors. So instead of going through the whole process again, I'll just state them here. One eigenvalue is 8, and an eigenvector corresponding to that eigenvalue is 1, 1. And so the meaning of this is that A times P1 is equal to 8 times P1. Now there's an infinite number of eigenvectors corresponding to an eigenvalue of 8. You can pick any one of them, right? Because all of those vectors get scaled by 8 when you do A times that eigenvector. And you just need to pick one of those vectors. All right, and another eigenvalue is 4. And the eigenvector corresponding to that eigenvalue would be 3, negative 1. And really, any scalar multiple of that would also be an eigenvector corresponding to the eigenvalue of 4. All right, so we've already covered how to find those eigenvalues and corresponding eigenvectors. Now, to diagonalize our matrix A, all you have to do is form your PDP inverse. So P, the columns are the eigenvectors. D, the values on the diagonal are the eigenvalues. And then you have to calculate the inverse of P to get P inverse. And notice the order is important here for the columns of P and the entries in D. Notice that the first column of P is the eigenvector P1 that corresponds to the eigenvalue of 8, and 8 is the first diagonal entry in D. So you can't just switch 8 and 4. If you do switch 8 and 4, then you have to switch the columns of P so that you still have that correspondence between the eigenvectors and eigenvalues. So the order really does matter when you're forming the columns of P and the diagonal entries in D. All right, another thing you can do is rearrange this equation to solve for the matrix D. And your homework will ask you to do that. And the way you can do that is multiply both sides on the left by P inverse, right? So the right side of the equation, you have P inverse times P, which is the identity matrix. And then multiply both sides of the equation on the right by the matrix P, because then you'd have P inverse times P, which is also that matrix. So that's how you could solve for D. And so that would give you P inverse multiplied by A multiplied by P. That would give you the diagonal matrix 8004. All right, let's look at diagonalizing this 3 by 3 matrix. So in the previous video, when we were finding eigenvalues and eigenvectors, we showed a 3 by 3 case. And I'll just state that here instead of going through the whole process again. So there's the eigenvalues and eigenvectors that correspond to those eigenvalues. And so each of those vectors are getting purely scaled by those corresponding eigenvalues when you do A times that vector. Once you have those, you can diagonalize A by doing P, D, P inverse, where the columns of P are P1, P2, and P3, right, those eigenvectors. And then once you've written your columns of P, you have to order D correctly so the values correspond to the vectors in P. Okay, so the first diagonal entry in D needs to be correspond to the eigenvector in the first column of P, and so on. For column 2 and column 3 for matrix P and D. Then you also have to find the inverse of P by doing the method we showed for inverse of 3 by 3s, augment the 3 by 3 identity matrix at the end of the matrix P and reduce it. And if you get the identity matrix on the left, that means it's invertible. Whatever matrix you get on the right after reduction, that is the inverse of P. Okay, so that's another previous video when we're finding inverses of 3 by 3s. All right, let's finish by looking at a non-diagonalizable 3 by 3 matrix. So if we were to attempt to find the diagonalization of this 3 by 3, well, first let's see what happens when we find the eigenvalues by doing the determinant of A minus lambda I equaling 0. You'd get this polynomial, and this has roots at positive 1 and negative 2. So those are your eigenvalues. And notice negative 2 has a multiplicity of 2. And we saw in the previous video when we're calculating the eigenvalues of a 3 by 3, you could have potentially for the eigenvalue of negative 2 to have an eigenspace that's two-dimensional instead of one-dimensional. That means the set of vectors that gets purely scaled by negative 2, that set could be a plane instead of just a line going through an origin. It could be a plane going through an origin. So you'd have to figure out two independent vectors that would form the basis of that eigenspace. We would describe all vectors that get purely scaled by negative 2. So first, for the eigenvalue of 1, calculating the eigenvector correspond to eigenvalue of 1 would be 1, negative 1, 1, or really any scalar multiple of that could be an option for an eigenvector corresponding to that eigenvalue of 1. Now we're hoping that the eigenspace corresponding to the eigenvalue of negative 2 is two-dimensional, but it's actually not. For the eigenvalue of negative 2, you only can get an eigenvector of negative 1, 1, 0, or any scalar multiple of that. So it's really just a line going through the origin is a set of all vectors that get purely scaled by negative 2 when you do A times those vectors. Now let's just verify this. If we take our matrix A and subtract negative 2 from the diagonal, which is really adding 2 to the diagonal, and we're solving the homogeneous equation, right? A minus lambda I, x equaling 0. That was our method for finding eigenvectors. Any vector x that solves this also solves ax equals lambda x. And we showed that in the previous video. So if you get the augmented matrix and reduce it, you'll get row 2 being a row of zeros, and the third row being 0, 0, 1, 0, and the top row being 1, 1, 0, 0. Notice in our above equation, ax equaling 0, or really a minus lambda I, x equaling 0, row 2 is just a scalar multiple of row 1. Right? It's scaled by negative 1. So when you do a row operation, you'll actually just get all the zeros for the second row. And then the first two 3s in the bottom row will turn into zeros, and the 3 will turn to a 1. And so you get that reduced echelon form there. And what that means is, right, interpreting that reduced echelon form, means x3 is equal to 0. That's what the bottom row is saying. And the top row is saying x1 is equal to negative x2. Okay? So you could let x2 be a parameter t, and then you get the eigenvector -1, 1, 0 as a solution to that equation, or really any scalar multiple of that because we have the parameter t. And so, zooming back out, we're trying to diagonalize the matrix A. We need to form PDP inverse, and P is a matrix consisting of your eigenvectors, but we're only able to get 2 eigenvectors. Now you might be thinking, well, we can do any scalar multiple of either of these vectors, so why not just pick another vector that's a scalar multiple of one of these? Well, if you do that, then you don't get 3 linearly independent vectors, and we know if you have linear dependence between vectors, then if you make those vectors form a matrix, that matrix is not invertible, because if you reduce that matrix, you wouldn't get the identity matrix because the columns would be dependent upon each other. They're not independent. So we're only able to get 2 independent eigenvectors. There are not 3 linearly independent vectors for this matrix, so therefore A is not diagonalizable. We can't form a matrix P such that P inverse exists. And one last note, you might be thinking, well, is this always true when you just get maybe 2 eigenvalues when there's a 3 by 3 matrix? Well, that's not necessarily true. It is possible, as we've seen before, to have an eigenspace that's 2-dimensional for just 1 eigenvalue. So if for lambda 2 we had 2 linearly independent vectors, then we would have had overall 3 independent vectors to form a matrix P. So it just depends. It doesn't, just because you only had 2 eigenvalues doesn't necessarily mean that it's not diagonalizable. You really have to always check for the eigenvectors. Are you able to produce n independent vectors for n by n matrix A, n eigenvectors, or are you not able to? If you're not able to, then you're not able to diagonalize your matrix A. All right, well, that's it for this video. Thank you.